In this video, I want to talk about some of the properties of cosets. When we deal with cosets in a group, we must keep in mind that every coset of that group is a subset of that group. So if I need to prove that two cosets are equal, I must show that they're equal sets. The first thing I want to show, if A is an element of the coset HB, then the coset HA is the same as the coset HB. Let's let X be in HA. Then we need to also show that it's in HB. Since I'm claiming H is in the coset HB, then we know A is equal to H1B, where H1 is an element of H. Let's let X be in HA. We need to show it's also in HB. Since X is in HA, we know X is equal to H2A, where H2 is in H. Well, we also know that H is equal to H1B. Since this is a group, I have my associative property. I can regroup this as H2, H1B. So now I have X is written to as an element in H, since H is a subgroup. I know it's closed under products, times B, which gives me that X belongs to HB. This shows me that HA is a subset of HB, and now I need to go the other way. Let's let X be in HB. Then we know that X is equal to H4B, where H4 is in H. Since we know that A is equal to H1B, we can also say that H1 inverse A is equal to B by multiplying both sides by H1 inverse on the left. That then gives us that X is equal to H4 times H1 inverse A. We can regroup, and since this is a subgroup, it's closed under products and inverses, so this is an element in H times A. So that gives me that X is in HA. That then showed that HB was a subgroup of HA, and since they're subgroups of one another, they must be equal. The next thing I want to show, the family of all cosets HA, as A ranges over G, is a partition of G. The first thing we have to show is that any two cosets are either disjoint or equal. Let's pick an element X in HA intersect HB, so it's in both HA and HB. So I'm going to show that HA is equal to HB. Since X is in HA, we know X is equal to H1A. And since X is in HB, we know X is equal to H2B, where H1 and H2 are in my subgroup H. This then gives me that H1A is equal to H2B, since they're both equal to X. Multiplying both sides by H1 inverse, I have that A is equal to H1 inverse H2B. So I have A is equal to an element of H times B. So I know that A is in HB, and by the property that I just showed, that means HA is equal to HB. So I've shown the first part of showing this is a partition. Next, I'm going to pick some element C of G, and I need to show it's in some coset in order to show this is a partition. Well, since H is a subgroup, we know it must contain the identity. And since the identity times C is C, we know that element C belongs to my coset HC. So therefore, the family of all cosets is a partition. The next thing I want to show, I'm going to let G be a finite group and H be some subgroup of G. If HA is any coset of H, there is a one-to-one correspondence from H to HA. So essentially what this says is that all the cosets of my subgroup H will have the same number of elements. So let's go about proving this. In order to prove there's a one-to-one correspondence, I'm going to need to start with a function. So we need a function f from H to HA. And the easiest way to define this is f of H is equal to H times A. So A is going to be remaining fixed while H varies over all of the elements in this subgroup. In order to show this is a one-to-one correspondence, I need to show both injective and surjective. Let's start with injective. For injective, we start by assuming f of h1 is equal to f of h2. That means h1a is equal to h2a. Multiplying both sides on the right by A inverse, we get h1 is equal to h2. So yes, this is injective. For surjective, every element of capital H of A looks like a little h of A for some h in H, in capital H. Well, f of h definitely maps to that. So this one's very obviously surjective. So this is a one-to-one correspondence. So we've shown that for finite groups and subgroups, all the cosets will have the same number of elements.